Hello and welcome to another lecture for Machine Design, ME 372. In this lecture, we're going to talk about static failure theories. The purpose of a static failure theory is to take a given stress state and compare it to a single value and predict whether the material fails or doesn't. Oftentimes, we'll plot the failure theory, as shown here in this plot and this plot here. In this plot, we show several failure theories used for brittle materials as well as materials that have unequal ultimate shear tensile strengths and compressive strengths. The idea of these plots is that if you plot the stress state and you're inside the envelope, you're safe and the material will not fail. If you plot the stress state and you're outside the envelope, you will fail. This plot here shows the von Mises ellipse, which is the most accurate ductile failure theory. It also shows in the blue shaded region the maximum shear stress failure theory. Over here we have a couple pictures of failures. Here we have a brittle fracture of a bolt in tension, and we can see that, as expected, the bolt failed in the threaded region where we would have a notch or a crack already initiated. Then down here we have a torsional failure, and we can see that this torsion has resulted in an extra piece of material hanging off here, and we get not necessarily a brittle fracture, but a torsional twisting type of stress as compared to this brittle fracture, which is a nearly straight plane. Here again we have a brittle fracture, and we can see the rough surface of the brittle fracture. We can see that this was due to some torsion because we can see that these lines here, which are the ribs and the splines in a splined gear shaft, are twisted. And we can see that they have deformed some before the brittle fracture actually occurred. And here we have the twisting of a large shaft. So again, the idea of a static failure theory is that it predicts failure by comparing the stress state to a single number. Typically, that single number is related to the tensile yield strength or the compressive yield strength. So to move on talking about static failure theories, again, the purpose is to relate a stress state to a single value of strength and predict failure. The difference between failure theories is often categorized by whether the material acts as a ductile material or a brittle material. And so the first step in selecting which failure theory to use or which failure theory is appropriate for the stress state that you're looking at is to determine whether the material acts as a brittle or ductile material. It's important to note that the material may be a ductile material, but over the region of interest of which you're testing, it may act as a brittle material. So it's important that we pick whether the material is ductile or brittle based on the particular stress state and the loading that over which we're looking at specifically, and not just classify the material in general. This also has to do with temperature. For example, some steels will act ductile in room temperature and above, but then in colder temperatures, the material acts as a brittle material. So when picking ductile or brittle failure theories, you need to make sure that you are looking at the situation in which your part will be subjected. So materials are classified as brittle if the strain at fracture is 0.05 or less. So 5% strain or less at fracture, and the material would be classified as a brittle material. And as you recall, the strain value used to compute the yield strength is 0.002 or 0.2%. So if for a brittle material, you'll actually get a significantly more amount of strain in a 0.05 than you will when you're computing the yield strength at 0.002. So this is one of those numbers that you kind of keep in back of your mind and that you remember when you're dealing with static failure theories. If the strain is less than 0.05, then you're brittle. And if the strain is greater than 0.05 at failure and the material stretches more than this 0.05, then you are classified as a ductile material. We'll focus a little bit on both, but mainly what we'll talk about in this class are ductile material failure theories. And we'll look at these three here. The first one is maximum shear stress, and this one is a very easy, very nice failure theory, and it's conservative. The distortional energy is a little bit harder to apply, but is more accurate and gives a better answer. This is overall the most accurate theory as long as the tensile and compressive yield strengths are equal. And this distortional energy failure theory has several other names, but they all result in essentially the same theory. It's also called the shear energy, von Mises-Henke, and octahedral shear stress. These are just essentially different forms of looking at the distortional energy failure theory. And the last one that we'll talk about is the ductile Coulomb-Moore, the DCM failure theory. And this is a good failure theory when you have different values for the tensile and compressive yield strengths. Then for brittle materials, many brittle materials such as cast iron don't have a yield strength, and failure is determined by the fracture or ultimate strength. And then a few of these brittle failure theories are the maximum normal stress, and this is the theory that you probably have been using in all of your analysis up to date. And we're going to actually see that this failure theory has its weaknesses. We'll discuss this failure theory first on the next page, just because it's one that you have been using and it has significant weaknesses. Then there's the brittle Coulomb-Moore, the BCM theory, and the modified Moore. These are two very similar and very good failure theories for brittle materials. So let's start now by looking at the maximum normal stress, and then we'll come back up and talk about these ductile material failure theories. So for maximum normal stress, also called maximum principal stress theory, failure occurs when the maximum principal stress is equal to the yield strength. So the idea of what we do is we rank the principal stresses. We rank sigma 1 as being the rightmost, sigma 3 as being the leftmost principal stress, and sigma 2 is the middle principal stress. Then failure occurs, 1, when sigma 1 is greater than SYT, or sigma 3 is less than negative SYC. So if our leftmost principal stress is greater in magnitude than our compressive yield strength, then we are considered to have failed. And if our rightmost principal stress is greater than our yield strength, we're considered to have failed. And this failure theory can also be based on ultimate strengths. And sometimes it is, because it's more of a brittle failure theory where you use the ultimate strengths more often as your failure criteria. If the maximum normal stress is ever used as a ductile failure theory, then you would be using the yield strength values here. Now, it's important to note that this theory breaks down when significant shear exists. So if we look at this example below, we'll plot more circle for the stress state shown on the element. So here I'm going to have a sigma 1 and a tau, and in this case I have a 0 tau. So my coordinates for my vertical stress are sigma 1, comma 0. And then here, the stress is on my horizontal plane. Again, there's no shear, and I have a compressive sigma 2. So I have sigma 2, comma 0, and I'm going to let sigma 1 equal sigma 2, but be a negative of it. So minus sigma 1, comma 0. Now look at the stresses on a 45-degree angle as shown. So if I come here and I plot my vertical point as sigma 1 and 0, there's my vertical line. Then I plot minus sigma 1 and 0, or sigma 2, and that's my horizontal line. This is my origin of planes. And if I plot the radius of this circle, the radius is actually sigma 1, or the maximum principal stress. And that means that my maximum tau is also equal to sigma 1, because the radius of my circle is my tau max. So this says that this material has as much strength in shear as it does in a normal stress, and that is typically not the case. We actually know that the shear strength is typically on the order of 50% of the ultimate strength. And so if you have any shear in your model, if you have significant shear stress, this failure theory breaks down and says you're safe when you are actually unsafe. So it's a non-conservative failure theory when your sigma 1 and your sigma 2 are nearly equal but opposite in magnitude. Then this failure theory will break down, because it predicts again that your radius of your circle is sigma 1, and so your tau max is equal to your maximum normal strength or normal stress. And this type of stress occurs in a cylindrical bar subjected to pure torsion as well. So if I have a shaft here and I subject it to pure torsion, then I get a pure torsion state here, and I get a similar reading, similar Mohr circle centered about 0, where again the tau max would be equal to sigma 1. For brittle materials which do not fail by yielding but by brittle fracture, this failure theory can be okay. So it's classified as a brittle failure theory, and it's okay, but it still has its weaknesses. Now this is the one you've likely been using as a failure theory up to now. But now we know better. We know this failure theory is not very good for ductile materials, and we know why, and it's because it predicts that the shear strength is much larger than it actually is. If we take this failure equation right here, sigma 1 greater than SYT and sigma 3 less than SYC, if we take this expression and plot it on a stress plot, we get the following. Here I'm plotting sigma 1 over SY, and here I'm plotting sigma 2 over SY. What I get when I plot that equation of the failure theory is this dashed line here. that forms this box. So everything inside this box would be considered a safe stress state. Everything outside the box is considered a failed stress state. Now what we have plotted here in this plot is real experimental data as to where a system failed. And we can see that up in this region here, the dashed line is a conservative estimate of the failure theory because most of the experimental data is outside of this. This is failed experimental data. And so up in this region here, it's not too bad of a failure theory. So if you have a tensile sigma 1 and a tension sigma 2, then you're going to be okay using this maximum normal stress failure theory. But if we look down here in this region where we have a tension sigma 1 and a compressive or a negative sigma 2, then all of these data right here are the failure data, and yet we're still predicting that we would have a safe stress state clear out to here when we actually will fail way in here. So in this quadrant here, where again we have a tensile sigma 1 and a compressive sigma 2, we overpredict the strength of the material, and this failure theory is unconservative and actually can give us significant error. So hopefully this provides you a summary and a good strong background in the maximum normal stress theory. You need to know this expression for the maximum normal stress theory. You need to know when it fails and when it's not a good failure theory. And you need to be able to plot this failure envelope and discuss it by knowing that these points out here represent failed stress states and points inside the dashed line would be safe stress states. We're now going to move on and talk about the second failure theory that we had listed here. It's actually the first ductile failure theory, and it's called the maximum shear stress theory, MSS, or the Tresca failure theory. This theory says that yielding begins when the maximum shearing stress at the point reaches a value equal to the maximum shearing stress in a tension specimen when yielding starts. So in other words, what we do is we take a tensile specimen and we stretch it, and the maximum shearing stress in the tension specimen, when we hit that point, when this thing starts to yield, the maximum shearing stress that we get at that point where yielding begins, when that equals the yield or the shearing stress at our point of interest, then we fail. So if we look at this, we take a tensile specimen and we draw the stress element for it. This is what the stress element would look like. We would have a normal stress P over A pulling on this stress element and no other stresses. So my vertical point is going to be given by 0, 0. My horizontal point is going to be given by sigma, 0. So I draw my vertical point here at the origin. I come out to sigma and 0 and draw my horizontal point. This is my origin of planes. Now we can see that the radius of this circle will actually be half of sigma 1. And that is exactly what this failure theory predicts. So in tension, we have tau max is sigma 1 minus sigma 3 divided by 2. Sigma 3 in this case is 0, so I have sigma 1 divided by 2. Then if I let sigma 1 be the yield strength, I get SY divided by 2, and we commonly call this SSY. So SSY is 50% of SY. Now the failure theory for this is given by safety factor as SSY over tau max, where SSY is 0.5 SY over tau max, and tau max is sigma 1 minus sigma 3 divided by 2. We can see that these 2's cancel out, and the failure theory results in SY divided by sigma 1 minus sigma 3. So the idea of what we do is we put in our sigma 1 and our sigma 3 here for our stress state, and we divide SY by that quantity, and if that quantity is greater than 1, then we're safe. If it's less than 1, we fail. So this is a very easy failure theory. It's very simple, and it's pretty accurate. So again, the idea is that you just take your yield strength, divide it by the difference of your two principal stresses, sigma 1 minus sigma 3, and you compute your safety factor. So some notes on this failure theory are that it predicts yielding, but it's only good for ductile materials. In pure tension, failure due to yielding is shown experimentally to occur at 0.577 SY. Here we're predicting 0.5 SY. And so this is actually a conservative failure theory, because the failure can actually go out to 57.7% of the yield strength, where this predicts failure at 50% of the yield strength. So this is greater than 0.5 SY, which implies the theory is typically conservative. Continuing with maximum shear stress theory, every stress element consists of three principal stresses. In plane stress, one of these three principal stresses is zero. These conditions generate 6 expressions that are used to plot the 6 lines in the maximum shear stress theory. So the failure equation that we're going to plot to get the failure envelope with the safety factor equal to 1 is given by this expression here. Sigma 1 minus sigma 3 is greater than or equal to SY. And that's when our safety factor is equal to 1. So for case 1, this is the region of sigma A greater than sigma B greater than 0. So here on my X and Y axes, I'm plotting sigma A on the X axis and sigma B up here on the vertical axis. So for this case, sigma 1 is equal to sigma A and sigma 3 is equal to 0. The failure equation reduces to sigma A greater than or equal to SY. So we get this line here. Now if we look at sigma A greater than 0 greater than sigma B, for this case sigma 1 equals sigma A and sigma 3 equals sigma B. And the failure equation reduces to sigma A minus sigma B greater than or equal to SY. And this results in this line here, this sloped line in this region down here. And then case 3, where we have 0 is greater than sigma A, greater than sigma B. So both stresses are compressive stresses. For this case, sigma 1 equals 0 and sigma 3 equals sigma B. The failure equation reduces to this expression and gives us this straight line here. And the other three lines are generated in the exact same way, except that sigma B is greater than sigma A. And then we would generate these lines here. So this is the failure envelope that we get for the maximum shear stress failure theory. Everything inside of this envelope would be safe, everything outside will have failed. We note that in this region here, this is the same failure theory as the maximum normal stress failure theory that we just looked at. But down in this region where we have a tensile normal stress and a compressive normal stress, we actually cut that box in half and we get rid of this extra area that was in the maximum normal stress theory out here. So plotting this failure theory with some experimental data, we can see that here this is the top curve, top portion of the failure envelope, and again we're conservative as these points represent failed stress states. Down in this region here, we are also conservative because this line is also on the inside of these failed points here. And you can see the difference in these points. The open circles are nickel, chromium, molybdenum, steel. The open square boxes are 2024 T4 aluminum. And then AISI 1023 steel is the black circle. And 3S-H aluminum is the black box. And these data come from your textbook. So this shows us that this plot is different than the maximum normal stress, again, only in this quadrant here and in this quadrant here, and it essentially cuts that box in half. The maximum shear stress is a very good theory. It's conservative and it's very easy to apply. So you need to make sure that you can draw this stress envelope again, and you need to make sure that you know the failure equation and can use this failure equation without having it given to you. You should be able to write down the safety factor expression for maximum shear stress. The next failure theory that we want to talk about is strain energy based failure theory. It's the distortional energy failure theory. And this is by far the most popular and most accurate failure theory for all stress states as long as the yield strength in tension and the yield strength in compression are equal. If you have a material such as concrete or cast iron where the tensile and the compressive yield strengths are different, then you need to make sure that you use a different failure theory. But in the strain energy failure theories state that yielding begins under any combination of stresses where the strain energy density of distortion at the point is equal to the strain energy density of distortion in a tension specimen when the stress in the tension specimen is equal to the yield stress. That's quite a mouthful, so let's break it down and make sure we understand what this strain energy density of distortion represents. Let's first talk about strain energy, then we'll talk about the strain energy of distortion. So strain energy is typically given the symbol U, and it's equal to the area under the stress strain curve. In this system over here, if we let P be applied to this axial rod of length L, we get a deflection delta. And the work done by P is P times delta, and we integrate P delta to get the work done in elongating the rod. And the work done on the rod, this W, is equal to the change in energy of the material. And this energy change is called the strain energy because it is derived from the strain configuration. So the work done here is the strain energy. And we can see that the work done is equal to capital U now, integral of P delta. And we know for an axial rod that the stress is given by stress equals force over area. So here we know that P, which is the force, can be written as sigma A. D delta is the change in length, and we can write that as L times the change in the strain. So now grouping terms, we have AL that can be pulled out of the integral, and we have sigma d epsilon, where epsilon here is the strain and sigma here is the stress. Now we know Hooke's law for 1D linearly elastic is sigma equals EE. So we can write the strain as sigma over E, and so d epsilon would be d sigma over E. We can make that substitution into the expression of the work, and we can get that the work then is AL sigma squared over 2 modulus of elasticity. So U is sigma squared over 2E, where we dropped the A over L term, and we're looking at the strain energy per unit volume. So this is the volume of the material. If we get rid of this volume, then we're looking at the strain energy per unit volume. And we can see that this results in sigma E divided by 2, which is exactly the area under the stress strain curve in the linear portion. So we've shown that the strain energy is indeed the area under the stress strain curve. Now, failure occurs when the total strain energy per unit volume in the stressed element equals the total strain energy per unit volume in a tensile specimen at the yield point. We want to look a little bit about what we call the distortional strain energy. Experimenters noticed that many materials remain elastic when subjected to very high hydrostatic pressures. Since hydrostatic pressures cause only a volume change and not a distortion, it was postulated that only the strain energy which causes distortion should be used and not the total strain energy, which accounts for the strain energy used to cause a volume change. And that's why we call this the distortional energy theory. So to say this in other words, what people found is that if you take a body and you subject it to equal pressure all the way around, so it has equal force on it in all directions, the volume will certainly decrease in size, but it will not distort. It will have a uniform volume change. And researchers found that that uniform volume change does not cause failure. So a material in a hydrostatic stress state, where there would be equal pressure on all sides, that material would compress and get smaller, but it would not fail. So that's the important thing to note. So in the development of the distortional strain energy failure, then what the goal is to find the strain energy due to distortion and the strain energy that causes the material to change shape and change its volume and shape. So the hydrostatic pressure will cause a volume change, which will not cause failure. But the distortion energy will cause the volume to distort and change its shape, which does cause the failure. And so here what we have is we have the total strain energy is equal to the strain energy that causes distortion plus the strain energy due to a volume change. And what we want to do in our analysis is solve for U distortion, because this is the strain energy that is going to cause failure in our material. So essentially what we do is haul U volume change to the other side, and we get U distortion of what we're looking for is equal to the total strain energy minus the strain energy due to just a volume change, or the hydrostatic pressure change, or an average stress type distortion. So graphically what this can be written as is, here's my total volume and distortion change, and so this would be a volume change in a distorted element due to sigma 1, 2, and 3, and that would equal the volume change, or an average stress on all of these faces, plus the distortion, which would be the difference from the sigma 1, 2, and 3 and the average stress. And so this is the distortional energy, or the strain energy component that we're interested in. We're interested in the strain energy component that causes my member to distort from its original shape. And now what we need to do is derive an expression for this distortional. To derive this expression, we'll come back to the work done in a unit cell, which we showed was U is equal to sigma times the strain divided by 2. We can write the total strain energy then as U1 plus U2 plus U3, where the 1, 2, and 3 are the three principal directions. So we're looking at all three directions in this case here. Then we can expand this as sigma 1 epsilon 1 over 2, sigma 2 epsilon 2 over 2, and sigma 3 epsilon 3 over 2. And this would represent the total strain energy in all three orthogonal directions and the principal directions. Now, we remember Hooke's law for 3D is given by this expression here, where epsilon 1 is 1 over e, and sigma 1 minus Poisson's ratio times the other two principal stresses, and then epsilon 2 and epsilon 3. This we're going to call equation 1, and we're going to take and substitute these expressions here for Hooke's law into equation 1 and rewrite U total. And when we do that, we can pull out a 1 over 2 modulus of elasticity and get this expression here. And we note that after substitution, the U total is a function of the normal stresses. It's a function of the sigmas only. So all of these are the sigmas, and this U total is a function of only the normal stresses. Now we're going to define an average stress as sigma 1 plus sigma 2 plus sigma 3 divided by 3. So this will be the average stress on the element. And we're going to substitute this sigma average into equation 2. So we're going to substitute sigma average into this expression to get a strain energy due to the volume change only. So making that substitution, we can get this expression here, which results in this expression here. And so this is equation 4, where we now have the U volume change, which is 3 sigma squared average over 2e, 1 minus 2 Poisson's ratio. So this is due to the volume change only. So we now have the total strain energy, and we have the strain energy due to a volume change. And from this, we can now compute the distortional energy. So now substitute the average stress squared into equation 4. Here's my average stress squared. I'm going to substitute that into equation 4, and I get the U volume change. And expanding this out, I get this expression here that is now in terms of sigma 1, 2, and 3 based on my definition of the average. So my U volume can be written as this expression now. And now recall that, again, the distortional energy is the difference between the total and the U volume. So we're going to come back, and here's our U total expression, and we're going to subtract from that the volume expression. And when we do that, we get this expression here for the distortional energy. So this expression represents the strain, or the distortional energy in the system. Nu is Poisson's ratio, E is modulus of elasticity, and we note that these are just the differences in the three principal stresses. And we note that if sigma 1 equals sigma 2 equals sigma 3, if all the three principal stresses are equal, then the distortional energy is 0. And that should be, because we would have a hydrostatic stress state at that point. So now let's look at putting this into a failure equation. In tension tests, then, failure in a member is determined by setting the strain energy due to distortion equal to the strain energy at yield in a tension test. And in a tension test, we'll have sigma 1 equals sigma sy, and sigma 2 equals sigma 3 equals 0. So my U distortion reduces to this expression here, because these two principal stresses would be 0. Then setting this equal to equation 8, we get U distortion is equal to this expression. And solving this expression for Sy gives us Sy is equal to this result here. And the safety factor equation is then given by hauling this to the other side and setting it equal to our safety factor. And so we have safety factor is equal to Sy over this denominator. And we often write this as Sy over sigma prime, where sigma prime is given by the square root of the differences of the principal stresses squared divided by 2. So this is a very important equation. This equation you need to commit to memory and make sure that you understand how it was developed. I won't expect you to be able to derive it, but you need to understand how it was developed and where it came from. And again, it comes from the idea of the distortional strain energy. And sigma prime is called the von Mises stress. And it's always a positive value. You can see in here everything is squared and then square rooted. So it's always a positive value whether you're in tensile or compressive stress. And the thing that it does that's unique compared to the other failure theories is it represents the complete stress state. And by that, what we mean is that it has sigma 1, sigma 2, and sigma 3 involved in the equation, where the other failure theory, the Tresca or the maximum shear stress theory, only had the maximum principal stress. It did not have all three principal stresses in the failure theory. And so this failure equation and failure theory is great because it includes all three principal stresses in the expression used to determine